All right, so as I mentioned last week, the plan for these weekly or daily sessions is to be more like office hours, more chance to just go through examples. So I'll usually start out like I would in class and just invite you all to ask questions. If you don't have questions, I may suggest an example. And if you feel like you've got everything you need, welcome to disconnect at any point. And once the questions die down, we'll just end the call and you can go about your business. So we'll start off with questions. I hope you've had a chance to watch the first batch of videos for chapter 10.1. Are there any questions you guys would like to talk about? And you can type your questions in the chat window, or you can just speak up. Either way would be fine. And I'll remind you, if you have no questions, feel free to just type in the chat window, no questions, so I know that you at least heard me. So Ian asks, I forgot that there were videos. Are they on Blackboard? Yes, if you go to Blackboard, there is a link to, on the left-hand side, to online course content. The video lectures will be linked there, as well as an updated schedule and any other information that you need. The discussion boards for people to post questions for their classmates or for me are there. The place where you would submit digging deeper problems are there, just about everything. And one of the things I'm hoping to do today, I'm about 60% through finishing grading the exams. I'm hoping to get those sent off via email to you all. And you'll also, I'll try to post a video with worked solutions to the problems so that when you get your exam, you can actually see them worked out correctly. All right. I'm not seeing any questions, so let's just do a couple of examples. And then if this prompts a question, that's fine. If not, then we'll wrap up. All right, so let's take look at a couple of sequences. Let's look at the sequence AN. So the nth term in the sequence is given by cosine of n pi over n from n equals 1, 2, and so on. And let's see if we can list off the terms and then figure out what the sequence actually approaches. Okay, so list A1, A2, A3. I think that's probably good enough. So we'll just list the first three terms and then find the limit as n goes to infinity of AN. All right, so we'll see how we can do this. For listing off terms, ultimately what we're doing is we're going to think about this as if it was a function. So we're going to be plugging in different values for n and then simplifying as much as we can. So according to our formula, A1 is going to be equal to cosine of 1 pi all over 1. And if you remember your unit circle, we'll draw a quick unit circle here. Cosine is always the x coordinate, and pi is 180 degrees. So we're talking about this point right here on the unit circle on the left side, and that's going to have an x coordinate of -1. So that would be -1 on top, all over 1. A2 would be equal to cosine of 2 pi over 2, which would be, let's see, cosine of 2 pi. That's a full circle, and so we're back on the right side of the circle. That means that the x coordinate is going to be 1. And then A3 would be cosine of 3 pi all over 3. And notice cosine of 3 pi means we've gone a full lap plus we've gone another pi. So that's going to be back to a -1 on top. All right, and if you're noticing the pattern here, it looks like cosine of n pi is going to just alternate back and forth between -1 and 1. And then the denominator is just counting up by 1. So A4 would be just 1 over 4, and A5 would be -1 over 5, and so on. Okay, and a quick note, often when you're dealing with sequences, you will come across things like a cosine n pi, and cosine of n pi is the same thing as -1 raised to the n power, because notice if I plug in 1 on the left-hand side, we got a -1. Well, if you plug 1 in the exponent, -1 to the 1 is -1. So these are actually the same. And then if you plug in a 2 to cosine n pi, you'll get a 1 on the left. If you plug a 2 on the right, you have -1 squared. And so the negative is going to cancel and you're going to get something positive. So this is a nice simplification that you can often make. And it's important to be aware that if this was a regular limit where we didn't have integers for n, we had some continuous variables, that would not be true. So that's only true if n is an integer. And so this limit that we're working on would not exist if n was not limited to integers, because cosine n pi just goes up and down over and over again. But because we're dealing exclusively with integers, right, the terms in the sequence are numbered off sequentially, 1, 2, 3, so on, then actually we can make this simplification. And so we could write an as -1 to the n over n. Okay? All right, so on to the second part of the question. We want to know what is the limit as n goes to infinity of an. And there's really a couple of different approaches that we can opt for. We can try to think of n as a continuous variable, and if that limit exists after treating n like it's continuous, then we could just use that answer. But as I just argued a minute ago, that's not going to work here because cosine n pi isn't really approaching anything. But the alternative is you can also use the squeeze theorem. Okay, so let's think about two other sequences, bn and cn. And what we'd like is to squeeze an between two other sequences. All right, so I'm going to try to find a sequence bn that is bigger than an for every single term. And I'm going to find a sequence cn that is less than an for every single term. And if I can choose those carefully so that those two sequences approach the exact same value, then what you'll find is that an has nowhere else to go, right? If you're bigger than something that approaches L and you're smaller than something that approaches L, well, you must approach L. Okay? So in this case, notice an is either has a -1 on top or a +1 on top. And so the numerator is always less than or equal to 1. The denominator is always just n. And so if I were to just write bn equals 1 over n, then notice the numerator is always going to be bigger for bn than it is for an, or at least I should say at least as big. So that would certainly work. 1 over n is going to be either equal to -1 to the n over n, or it's bigger. All right. So we could make the same sort of argument with the denominator. Sorry, not the denominator, with cn. Can anyone think of a sequence that's guaranteed to be smaller than every term in this other sequence? So again, thinking about the numerator, can you think of a number that's going to be smaller than both -1 and 1? Not all that hard, right? Certainly -2 would work. -3 would work. But the largest number that would work would certainly be -1. So -1 over n is going to be smaller than -1 to the n over n, because -1 to the n just alternates back and forth between -1 and 1. All right, so with that in mind, let's take a limit of each of these. What happens as n goes to infinity with bn? Well, the denominator gets bigger and bigger and bigger. The numerator stays fixed, and so that's going to approach 0. And if we apply the same limit to cn, the same argument will hold, except the numerator is negative this time, and so that has to approach 0 as well. And so we can say, by the squeeze theorem, the limit as n goes to infinity of an must be 0. It's smaller than something that's going to 0. It's bigger than something that's going to 0. Well, if it has to stay in between, then there's nowhere else for it to go. And you could visualize that as follows. So -1, well, let me first map out the terms for an. So this horizontal axis is going to represent n, and then the vertical axis is going to represent the terms in the sequence. So when n was 1, we had -1. When n was 2, we had +1/2. When n was 3, we had -1/3. And you'll see that the pattern continues. This one's just bouncing back and forth. If you look at the Bn terms, they're going to be something like this. They're going to be equal for all the terms that had a +1 on top, and they're going to be greater for all the ones that had a -1 on top. And if you look at the terms that had a all the Cn terms, they're always negative, and so they're the same thing, but reflected down below. And so graphically speaking, you can see that there is this shape that corresponds to 1/n. There is a shape that corresponds to -1/n. And if you're trapped in between those two curves, you must go to 0. All right, any questions about that one? All right, well, not hearing any so far. Let's do one more example. Let's look at the sequence. How about an is going to be equal to, let's do n squared minus 2n plus 3 all over 2n squared plus 4n minus 6. Ooh, let's not make that a 6 because that makes the bottom just double the top. Let's make that a 7. Okay? So there's the sequence. And we could certainly find some terms in this sequence. We could plug in n equals 1, 2, and 3. And so we'll do that really quickly. A1 would be 1 minus 2 plus 3 over 2 plus 4 minus 7, which is going to be a 2 over -1, so -2. A2 would be 4 minus 4 plus 3 all over 2 times 2 squared would be 8 plus 8 minus 7. So that's going to be 3 over 9, 1/3. And notice this one, it's a little harder to see exactly what the pattern is. We could keep writing out terms, but because the function that we're using to calculate the individual terms is a little more messy, it's going to be difficult to really see exactly what the next term is going to be without taking actually just the long route and plugging in different values of n to that expression. Okay, so we could keep writing that, but I don't know that that's going to help clarify things too much. So the next question is, what is the limit of the sequence? And in this case, we have a polynomial on top and a polynomial on bottom. And I think if this was a continuous variable n, or continuous variable x instead of n, then this would be a much easier limit than the one that we're dealing with here. So let's use our theorem from chapter 1, which said that you can treat these limits of sequences like regular limits as long as the limit actually exists. And so we're going to assume the limit exists for now. We'll then verify that it does actually make sense that the limit exists. And then if it doesn't exist, then we'll have to back up and try something else. So let's look at the limit as x goes to infinity of the same function, x squared minus 2x plus 3, all over 2x squared plus 4x minus 7. And now for a limit like this, the first thing you would probably want to do is try to plug in. But notice here we're just going to get an infinity on top and an infinity on the bottom, which means this is indeterminate form. And if you recall from Calculus 1, indeterminate forms don't mean the limit doesn't exist. What it means is we can't tell yet. You could have the numerator growing much faster, which means this would go off to infinity. You could have the denominator growing much faster, which means this would go off to 0. Or you could have them growing at roughly the same rate, meaning that this limit's going to approach some constant. But just plugging in and seeing that we have an infinity on top and an infinity on the bottom isn't enough information to tell which of those three things is happening. All right, so at this point, there are a couple of different strategies you can use. The one that I prefer is when I see a polynomial on top and a polynomial on bottom, I try to multiply the fraction by 1 and choose the power of the fastest growing term when I'm deciding what form of 1 to multiply by. In this case, notice x squared is growing fastest on top and it's growing fastest on the bottom. And so what I'm going to do is I'm going to multiply by 1 over x squared. Over 1 over x squared. So at this point, we've multiplied by 1, which means we haven't changed anything. But if we do this carefully, we might actually see that it gives us a different perspective on the limit. So let's distribute the 1 over x squared through. And we will have, let's see, 1 over x squared times x squared will give us a 1. The next term will have a 2x over x squared. So one of the x's will cancel, and we'll have a 2 over x. And then we'll have a 3 over x squared from the first term. And if you look at the bottom, same process, 2x squared over x squared, the x squareds cancel. 4x over x squared, one of the x's will cancel, so it'll be just a 4 over x. And then we'll have a 7 over x squared, and I think I lost a plus sign there. All right. So we've multiplied through by top and bottom, by 1 over x squared on the top and the bottom, and you'll notice now that if you were to plug in this term, 2 over x, well, its denominator is getting really big, and so it wants to go to 0. 3 over x squared, same thing. The denominator is growing, but the numerator is fixed, so it wants to go to 0. And if you look at the bottom, the same thing is going to happen to 2 of the terms as well. And so if all of those terms are approaching 0, the only ones that don't go to 0 are the constants, and so we're left with just a 1 over 2. Okay, so the terms in this sequence are approaching 1/2, and you can actually graph out the terms in the sequence. In fact, why don't I do that really quickly? You just give me a second. All right, so our sequence was n squared minus 2 times x plus 3 over 2 times x squared plus 4 times x minus 7. And let me zoom out just a little bit here. All right, and so you notice as you plug in larger and larger values of n here, the y values are getting close to something. And if we plug in 1/2, that seems like a very reasonable candidate based on the graph. Okay? All right, so that's 2 different approaches for finding limits. One approach is we treat it like a regular limit, and that only works if that limit exists, which in this case, we did show that the limit was equal to 1/2, so we can be confident that it exists. The other is we may need to use another sort of technique like the squeeze theorem to try to evaluate the limit. And in that case, you're comparing to 2 other sequences and trying to squeeze it in between them. And if those limits both exist and they both approach the same thing, then we can conclude that the sequence in the middle must as well. All right, so let me bring back up the chat window. Are there any questions about this example? All right, some no's from Bennett, no's from Ian, no's from Joseph. Not hearing from the rest of you, but I'm going to hope that means there's also no questions there. Would you guys like to do another example? If so, go ahead and use your microphone and actually speak up. Otherwise, maybe we'll just wrap up here and let you get to working on some of the web work and the digging deeper problems.